All right, are we ready to start today? So we're going to do unit 3 today, or start on it, and really start trying to look at how a CPU works here. What we're trying to do is, over the next couple of weeks, we'll be taking stuff we build in the Raspberry Pi actual digital circuits there, and we'll build up more complicated circuits up to an adder, which will like take two 4-digit numbers and add them together and produce the result. We'll talk about how you do it and how you build that so you could do 16 or 32 or 64-bit numbers there. And then we'll also look, so that'll be on the hardware side, kind of the lab side. And then at the same time, we'll start at a CPU and try to break a CPU down into parts here and get down to like the adder part and the circuitry part, so that hopefully within a couple of weeks, you can kind of have a visualization of how does the wires and the CPU actually add numbers or execute instructions and stuff like that. That's our goal, is to get a better understanding of how does this computer actually work, and so what is the magic underneath the hood of this. The readings this week are just chapter 3 of the text, so I'm going to bring that up here and kind of walk you through that today. With that, we'll do a number of things in the exercise. So you might want to go to exercise 3 and bring that up here. And we'll be working on that and walking through quite a bit of that today. So you might want to go there. And again, remember just to make your own copy of it. I'm not signed in, it looks like. Okay. Make your own copy of the exercise. And we'll look at that. Okay, but I'm going to start with the textbook. So chapter 3 is really talking about the processor elements, and by processor, we're really looking at the CPU here. We're focusing on a simple kind of architecture with a single CPU. Nowadays, most computers are running on what we call multiple cores, which will be multiple parallel CPUs. But again, under the hood, each one is very similar to like what we're looking at today. So you can just imagine that in today's CPU, we're going to duplicate this, CPU multiple times on one chip here to have multiple cores. So I think a lot of this is going to be review for the first part. So we'll see. I mean, I think a lot of this is just kind of basic stuff you probably learned, I don't know, somewhere. Certainly if you took CS principles. So we're going to talk about, what is a processor and what makes up a CPU here. And so it has a control unit here, an ALU, and some registers. So that's the whole CPU. And it's going to get stuff from memory or input-output devices and stuff like that. So this is our CPU here. But again, so hopefully you've seen that. Now what we're going to do is we're going to dive a little more deeply into this and like, what does this control unit do? What does the ALU do? How do, why do we call it an ALU here? And what's the difference between a register and memory here? So let's talk about the control memory or unit. So later on, we'll deal more with memory. We'll talk about how memory, actually works here. But just know that there is some random access memory that's outside of the CPU here. There's also often, besides memory, a cache of memory that's very close here. And then there's the registers here. One thing to keep in mind is like kind of how fast we can get to certain places here. So like, even though these just show these lines, some of these are a lot faster than others for this. So like let's say you're on campus here. So a register would be like something in this room that you can just grab and grab within like 2 seconds, anything storage in this room here, where this RAM is anywhere on campus, for example, anywhere. So, this might be in Cedar. So, I mean, that's only 10 minutes away. You can go down and get it in 10 minutes, come back. But it's this, if I asked you to get something and if we're in this room, it would be much easier to get than if it were in the apartments or in Cedar or something like that, right? Plus, you have to go out in the cold. And in our world, cold is like over the network. You have to get off of the chip, which is just a pain here. So there. And so we'll also often have caches in here. And again, we won't talk too much about caches, but a cache is like when you come in, if you have your apartment or if you have your dorm, you will put stuff you might need in your cache. Like often, if you have a backpack, your backpack is like your local cache there. And what you put in your backpack every day is what you think you're going to use that day. And so you're going to bring that in so it's closer. And it may not be in the same room here, but it may just be in the same building or something like that. So it's close for that. And then besides this, every once in a while we'll have to write to disk or get things over the internet. And that's like, besides on campus, that's like trying to go downtown or trying to go to Floodwood or something like that and get something from a different city. So that's a long way. Just so keep in mind that although we have these little arrows, some of these arrows are very small and some of these arrows are much bigger. So going to a register is very fast in this same room on our same chip. This is all one chip, these 3 parts on the left, where this is on a different chip. And as soon as we go to a different chip, that's like a different building we have to get to. So, okay, so random access memory, again, is on a different chip somewhere else there. Now, we will keep track of some things on our own chip, and one of them was a special register or special storage called a program counter. So we'll always keep track of a program counter, and we'll keep track of where we are in our little local area memory, our registers and stuff for our codes here. And then we're going to do what's called the fetch execute cycle. And you probably have heard of this before with computers, where we're going to fetch an instruction. We're going to execute that instruction, increment the program counter, and fetch the next instruction and implement it. Now, this is a little more complicated here. We set the program counter initially. We fetch the instruction that's pointed to by the program counter. We decode that instruction. And then there's 2 types of instructions. One is a branch instruction where we just have to update the program counter and go to the next instruction. So we jump to a different spot. Another one is if it's not a branch instruction, we execute that instruction, and then we always just add 1 to the program counter and go over here. So we're going to go through this fetch execute cycle and walk through that some today here. This is trying to talk you through a simple example of how we'll do this sort of stuff. So this is how we're going to try to add 2 numbers together. And again, we'll try to fill in these black boxes a little bit more here. But again, we're working with registers on our chip. And they're talking about this old 6402 processor. So we have 8-bit registers. So we have 8 bits here and 8 bits here. And we have what is called a multiplexer here, which combines these and generates a new 8-bit instruction. And again, this is what we'll do. We'll actually build a 4-bit sort of stuff on our boards. We'll wire up. So we have 4 bits here, 4 bits here, and then we'll generate 4 bits as the output. But this is 8-bit, and I don't think you've ever heard of an 8-bit computer. So you may not even ever use a 32-bit computer. Nowadays, all computers are generally 64-bit computers out there. So that basically means the size of this register is 64 bits, and this one's 64 bits. But again, the concept of it is not that much different between 4 bits, 8 bits, 64 bits here. We have binary number here, we have a binary number, and we're bringing it together and we're outputting it. And again, these are all going in and out of registers. So they're all on our chip here, which again, we have to do. We can only do things on our register because again, we'll see that when we have our circuit. We need the electrical signals to come and combine in the right ways for this here. So let's talk about the ALU here a little bit for this. So this is an example of an ALU for subtracting two values here. So we're talking about A minus B here. A minus B is what we're trying to do. Now, one thing we will do in computers is that we don't want to wire up too many different circuits here. And so we don't want to wire up a circuit for adding and a different circuit for subtracting. So we're going to convert every adding or every subtraction into adding for this. So we know that to add, to subtract is just to add a negative number. So we just need a negative number. Now, one thing I'll just point, I'll be jumping here a little bit. We will be talking about binary numbers. So just remind yourself, you know, these are our binary numbers and these are the decimal equivalents here. And so this is the first digit zero is, you know, this is zeros, all zeros, and then this is a one. Now it's binary. So if we add one to that, we get two. So, and a two is carried. So this is a 2, 1, 0. Wondering if I have, yeah, if I have a binary shirt. I don't think I want a binary shirt. I have a binary pun shirt, but I don't think I wore it today. So, and this is a 3. So a 2 and a 1 is a 3. This is a 4. This is 5 is a 4 and a 1. So these are binary numbers. Positive binary numbers. Now, there's a way of representing negative numbers in binary, which one way is called 2's complement. So this first digit here is, if it's 0, it's positive. If it's 1, it's negative here for this stuff. And so we can have positive and negative values here by just saying the far left digit is either a positive or a negative digit, and then have the rest of the digits the same. So this is how you'd represent 0, 1, 2, 3. But this is how you'd represent like -1, negative, or I mean, -8. And so it is the opposite of this. So while you might think this should be -1, it's actually negative. And again, as if all these were 1, -8, -7, -6. So it's kind of a weird representation. And the computer is actually using that here. We are taking the right value, the B that we want to subtract. We're putting this through an inverter and inverting all the bits and feeding that into the multiplexer here. And then we're sending that up here. And then we're taking the register A. So we're taking register B and register A here, putting them both into an 8-bit adder. And again, we won't be creating an 8-bit adder, but we will wire up a 4-bit adder here. And then the result will be stored in here. Now, one of the challenges going to be with these circuits is that they seem to just go in loops, and you can't just run a circuit in loop all the time. The electricity will just zoom around and, you know, kind of average itself out, you know, wear itself out almost. And so what we'll have here is a clock. The C is a clock signal here. And again, we'll see this. So when we activate the clock signal here, that will kind of open up the adder, activate the adder here. So we'll have this value here and this value here ready to go. And then, but it won't actually produce the output until we do the clock signal. The clock signal go from 0 to 1. And when it does that, or, you know, 0 voltage to 5 voltage, when it does that, it'll activate the adder circuits and then produce this output here. So we'll talk about this clock circuit. We'll also talk about we might have some other flags here. Sometimes we'll have a carry or a negative or a negate. There might be some other outputs here besides the actual number for this. Okay. So that's how we're going to be doing the this operator. So in order for programming this, we're going to have to get low level. Now, sometimes we teach this course the whole semester, we just do assembly language and low-level programming. We are not going to do that here. We're going to just spend this week, we're going to do some assembly language programming, and we won't do it anymore other than this week. So this is the only week we're going to look at assembly language programming, stuff like that. Some people really like assembly language programming. It's very low level. It's kind of fun to see. But again, it is kind of persnickety, I would say. Of course, I'm really old, so I use terms like persnickety. So what are our commands that we're able to use? And again, we're going to start with the old commands here. So we're going to have an add and a subtract command to add two elements here. We're going to have some increment commands to increment or add registers here. We're going to have an and, an or, and an XOR operators, and some other operators like this. So we'll have some low-level commands like this, and there might be different versions of this here. So this might say add register D with a carry. This might say subtract register B with a carry here. So sometimes they'll have slightly different meanings here when we look at them. And there might be more than what's actually shown here for this. Okay, so rather than going through this stuff, let's jump into the exercise and try to work through some of this stuff. So again, go in here, go to the exercise, click on that and open up your exercise. Make a copy of it here so you can edit it. First, we need to kind of do a little more complicated ands and nots. Last week we did single digit or just values with like an and. If one was true, another was true, what is the result here? Now we're going to convert that into binary digits and do what's called bitwise operations. So let's just talk about not. So if this is our number 0, 1, 1, 1, we're going to do not or negate that. So what that means is that we're going to do it bitwise. So if this is a 0, the opposite of 0 is 1. So the result is going to be a 1 here. This is a 1. So what is the opposite of a 1? It's going to be a 0. So again, bitwise means we're going to go through each bit here and negate it. So if it's a 1, it becomes a 0. If it's a 0, it becomes a 1. So your job is to create your own example here. So you have to put your own binary digit here. So make up some binary digit here. And negate it. Then what is the opposite of that? So again, we do what is the opposite of all? I'll start at the right. The first digit is 0. So that would mean this should be a 1. And again, don't do my example make it different. Just create your own example here. So again, in my example, this is a 1. So the opposite of that is a 0. This is a 0. The opposite of that is a 1. This is a 1. So the opposite of that is a 0. And again, if I were to do a different one here, if I were to make this all 1s, the result is all 0s. Not value. So again, we are going to define these values. And again, in the operating code, there will be commands for those. So like there'll be a bitwise and a bitwise or, and a bitwise XOR. And again, those will help us with some of the math to find like the inverse and stuff. For example, if we looked at this 8, -8 here is just the 1, and then the other 3 digits are the bitwise not of that. here. So it's a negative, but then this is a bitwise not of that. Okay, once you get the not, then you can do the and. So again, with and, we need two things like a true and, if we say is x less than 10 and x greater than 5. It has to be both of those for it to be true. So something that's true, one part is true and the other part is true, then it is true here. What that translates in is that if the truth table is if we have two ones, then the result is 1. So here, if I look at this one, the first digit 1 and 1, then the result is 1. But if I have a 0 and a 1, if I have any sort of 0 there, any sort of false value, in our cases, 0 will always be related to false and 1 will always be related to true. So if I see a false and a true, then the result will be false. 1 and a 0 is going to be 0, and a 0 and 0 is 0. So again, I do bitwise. Each bit I handle one in a case-by-case basis. And again, your job is to create your own bitwise example here. And again, it has to be binary, so zeros and ones. And you need two of these examples. And then go do your bitwise and operation. So again, it's only true if both of the bits are 1. So this is a 1, this is a 1. So this would be a 1. And that would be the only one. All the rest of these would be 0 in this case. And again, you can try different values in here. You do. And the last one to do is the next two is the OR here and the XOR. I'll let you do a couple and then we'll talk a little bit about the XOR. We got caught up on grading and graded some stuff. First 2 weeks, you don't count anything as late. So just remind yourself that when you do these things, you want to submit them. You have to go into Brightspace and do a submit and submit the document here. We will let you resubmit. So if you submit something that's not quite right, you get some points off, you can often resubmit it. But we do, I know a number of people just haven't submitted anything for the first 2 weeks. We really need you to be submitting work here. So as you do it, or even if you don't get it all the way done, or if you need help, you can always submit it and then ask for some help and then resubmit it for this. So try to make sure you're submitting every week. Things are due on Sunday night, and Monday we'll try to start correcting things. So, okay, so you did the OR, hopefully, and an OR means, again, you can either have a 1 or 0 or both. Fine. Now, what is an XOR? We take two things, and these what's called an exclusive OR here, where it's 1 if and only if one of the bits is 1. If they're both 0, it's 0, and if they're both 1, it's 0 here. So again, if they're both ones, if they're both true, then it's not right. It has to be one or the other. So 1, 0, and 1 and a 1, that's a 1, or a 1 and a 0, that's a 1. But again, if they're both zeros or they're both ones, the XOR is different than an OR, and it will do that. So again, create your own XOR ones here also. And then we're going to talk about assembly language here. So again, the textbook talks a little bit about this assembly language and walks through some simple assembly language things. And then talks about registers and it talks about just three registers, A, X, and Y, which were in this initial 6502 idea. And then they talk about these different assembly language commands. They're talking about like doing something with registers A and X or B and X here, or different options that you'll see. So one thing we'll talk a little bit about is the size of the instruction set and the complexity of the instruction set here. We'll start with very simple instruction sets here, but some computers have moved to very complicated instruction sets here. One of the things that we'll see is that when we get to more complicated instruction sets, it'll take multiple ticks of the clock to execute an instruction. We'll tend to talk about just every tick of the clock you can do it. So we'll do a fetch on one tick, and then we'll do an execute on another tick of the clock. So actually two ticks of the clock, fetch, execute, fetch, execute. But in more complicated instruction sets, you may have to fetch, check the addresses, and then fetch again what's in the addresses, and then execute. So it might be 5, 6, 8 in ticks of the clock to do a complicated instruction. So there's always debate where is it better to have simpler instructions where you might have to write more of them, but you can run them faster even at the same clock speed. You can just you don't need as many ticks of the clock to do them. Or is it better to have complex instructions set so you don't have to have so many of them for things? So okay, so let me see. Okay, I'm not going to get into this. So I wanted to get more into assembly language here. So we're going to do in part 2 this stuff. You may have remembered this. So I think most of you have had CS principles in the fall, but some of you are taking it now, possibly. So not if you've had CS principles yet. The 1001 class, the app development class. Some of you've had that. So yeah. And that's okay. But again, some of this will be familiar from that. We're going to work with this simple 4-bit computer here. It has a couple of registers. It has something called the instruction counter, which just tells us what address to load for the next instruction. The instruction register, which is the actual instruction we want to execute. And then the accumulator, which is our main register that we are working on, where we store things from. And this is our assembly language. It has a very small assembly language here. We can have a load A here or load B. So that'll load a value of data location. So if we say load A 00011, that'll load the value of location 0011 into the accumulator. If we say load AB, it'll load variable B into the accumulator here. Store a STA means, like if we say STA 0011, that means store whatever in the accumulator is to this location in memory. So we'll load that memory location into memory. Store STA will store that whatever's in the accumulator to that location. And again, we can always specify either a variable or a memory address directly for this. We can say add and specify a memory address or a variable, and it'll add whatever's in that memory address or that variable to whatever's in the accumulator. Subtract, multiply, divide. Print, just print something out here. And input is input. We can declare a variable, which will store a value in a variable for that. So let's try this out. If you go here, you can click on any of the links that say 4-bit computer. And I'll open it up here. I don't know. break this down, I think, into two screens here. Let's see if I can get this to fit there. Okay. So here's our 4-bit computer thing. I'm gonna take this assembly code here. And I'm just gonna grab this one column, and I'm gonna hit copy. I'm going to go to my editor here. I'm gonna paste that in. So I'm gonna grab, you can actually do this one too if you want, but I'm just gonna do this in the start. This is my assembly code. I'm gonna paste it in here. Assembly code is semi-English, so I can kind of read through and says variable A stored A, this value, store 2, store in variable B, store 1, load A, I load in the accumulator variable A, add whatever's in the accumulator to B, and store the result of the accumulator in B. So that's and print out B. So those are my commands. But we're going to have to convert these into machine language, low-level language. So we hit the assembler, and this is the actual binary that it's generating here. I'm going to roll that back up to a bigger screen, I think, so we can see that. So I'm going to go down to this load A here. And break it down. This is the command. It's 8 binary digits here. It's divided into 2. The first 4 are the command. And over here, this is the command. So I can look at 0001. So I go over here at all the machine code one. I find a match for that. That's this one. It's load A. So again, load A is converted to 0001 here. And then this is the memory. The second digits are the memory address out here, 1000. And again, up here, I declared a variable A, and I stored binary 2 in it. And it set aside memory location 100 for A, and it stored that value in here. So that's what it's trying to do there. And again, so each one of these here's my add command, store command, and I can translate those over here into the binary thing. So there's always a command on the left side and then a address on the right side. So I've assembled it. Now I'm going to load it in. And this is my little processor down here. If I hit load, now everything's 0 right now. I'm gonna hit load. It'll load the instructions into the left-hand side and the data into the right-hand side here. I thought, I kept wondering, I thought this was loading binary 2, but this is actually decimal, load 10 into this. So this is actually a decimal number 10. And so decimal number 10 is an 8 and a 1. I mean, a 1 are 8 and 2. So this is decimal 10 in binary. So it actually converted this from decimal into binary. That's why it looks different. Okay, that makes sense. Okay, so here's my instructions here. And again, it's basically just these 4 instructions. And then this loads in. Here's my initial memory here. 10 is stored there and 1 is stored here. This is A and this is B values. Now my instruction, the first instruction I'm going to run is instruction 0 here. That's my instruction pointer. So I can do a fetch. And it's going to go out and fetch instruction 0 and read it into the registry. And it's going to increment the instruction counter. So next time I fetch an instruction, I'll fetch the next instruction here. So, and here's my accumulator for this. So it's fetched. Now I'm going to execute. The command is 0001, which is load memory address A, load 100. So it's going to load in whatever's in this value into the accumulator. So if I hit execute, it has loaded that into the accumulator. Now I'm going to hit fetch again. And again, this is called fetch execute cycle. So I'll go back and forth. I'll fetch, I'll execute, I'll fetch, I'll execute. So I'm going to fetch. So it'll get this next instruction, instruction one, which is this one, and loads it into the instruction register here. Here's my instruction I'm going to do. And now if I hit execute, it'll execute that. So that is my add, whatever's in B, which is a one, add one to the accumulator. So it'll add this and the accumulator together and should come up with an 11. So execute made this bigger at 11 now. Now, last time when I hit my fetch, it also added the instruction counter. So now I'm down to this, the third instruction here, instruction number 2. So if it fetch, it'll get that instruction, which is store, which will store the accumulator into memory, into variable B, which is this memory location. So I can execute, and it'll stored this out here. I can, and again, the next instruction fetch, and then execute, and then it will, the last instruction is print. It'll print what's stored in B up here. So this is in binary, so it converts that to decimal and prints it out here. So what's basically doing is we're taking 10 plus 1, and we get an 11 for this. So that's what we're going to want you to work through a couple times here for this. So we're going to take that. We can take this and figure out what the output is. So take that command. Again, you can copy this code here, copy that code, paste that into the editor, not the monitor, just the editor, and then you have to hit assemble, and it'll update the assembly language. Then hit load, it'll load it into the little computer down here, instructions in the data, and then you can hit fetch execute here. So I can hit fetch. I'm going to hit restart. Oops. No, I'll just hit fetch, execute, fetch, execute, fetch, execute, fetch, execute, fetch, execute, fetch, execute here. I think I didn't reset something. I'm going to try to reset this again. So let's try this again. Okay, I ran the assembler, I ran the loader. I then want to fetch. Yeah. I think my instruction pointer was the wrong thing. So if you do this once, hit reset, type in Y, and then load in the next program. So what is this doing? If I just look at the code here, it's loading 10 into variable A and loading 0 into variable B here. It sets up those two variables. A is 10, B is 0. It then loads A into the accumulator, and it multiplies the accumulator by A. So it'll multiply 10 by 10, and then it'll store the accumulator back in B and print out B. So if I run through this, the first thing it's going to do is load A, which is 10. Execute that. It loads 10 into the accumulator. You got to kind of get used to, and again, sometimes I like to just keep a little binary printout here, so I can know 10 is 1011. That's 10. So when I'm looking at this, I can say this is 10, but it actually did this. So sometimes I just keep a little cheat sheet of binary codes. If you're old like me, you have a lot of the binary codes memorized already, but you may not have memorized binary codes as much as you want. If you're bored someday, that's a really fun activity. So if you're thinking, I'm getting tired of social media, I'm going to just memorize binary today. Do that. That's a fun activity to do. My son memorized pi. I thought that was exciting. Well, I memorized pi. Why don't memorize the first 256 binary digits? So you just have them off the top of your head. So just an idea. Okay, sorry for the digression. Okay, so we loaded 10 into the register. Next thing, we're going to multiply A, which is also 10, by the accumulator, which is 10. So we're going to multiply A. So we're going to load the next instruction, execute it, and it's going to multiply 10 times 10 and give us 100 here. So this is 100 in binary. Now we're going to store that in B. Notice that B, again, B here is being stored in this location. This is B, and there's nothing in it. So we're going to fetch B, fetch it and execute it, and it stores 100 into B. Now we do one more fetch, and it'll print out and execute, and it'll print out 100. So again, this code, 2.1, is just taking 10 multiplied by itself and storing it and printing it out, storing it in B and printing it out. So your job then for 2.2 is to take this code and modify it so that it takes, it adds, what is that? 1100. 1100. It adds 6. It takes 6. It takes 6 and adds it to itself. The result should be 12. So the result should be 12 here, 1100. So see if you can change this code so that it adds to itself. And again, these are different commands. Load into the accumulator, store whatever the accumulator is, and add, subtract, multiply, and divide, and print. Whoa. I'm going to play a little bit of this video. This is a PBS video. I think it's targeted to like first year college, or like I think it's really targeted to high school, like computer courses, like where we like CIS principles taught in a high school setting. But I think it's still pretty good here. And you have to watch the video and answer 2 things about it. Let's just bring up the video. Yeah, I'm going to turn up the volume just a little bit. Talk about that. So this comes from the whole crash course in computing.
Hi, I'm Hank Green. Welcome to Crash Course.
Yeah, we don't want to talk to you right now. Sorry. Which has a whole bunch of videos on all sorts of computer. Well, they have crash courses on everything. I want their playlist that's just the crash course on computing here. Here. Which walks through a lot of things, and we'll jump to different parts of these stuff here. So this is part of the whole crash course stuff.
Hi.
Yeah, Hank, you're still there. Okay, but we're just doing this first one.
From last episode, the computer memory looked like this. Each address contained 8 bits of data. For a hypothetical CPU, the first 4 bits specified the operation code, or opcode, and the second set of 4 bits specified an address or registers. In memory address 0, we have 00101110. Again, those first 4 bits are our opcode, which corresponds to a load A instruction. This instruction reads data from a location of memory specified in those last 4 bits of the instruction and saves it into register A. In this case, 1110 or 14 decimal. So let's not think of this memory address 0 as 00101110, but rather as the instruction load A14. That's much easier to read and understand and for me to say. And we can do the same thing for the rest of the data in memory. In this case, our program is just 4 instructions long, and we've put some numbers into memory too, 3 and 14. So now let's step through this program. First is load A14, which takes the value in address 14, which is the number 3.
Okay, so this is a little more complicated of a system, but similar. Again, same sort of 4-bit instructions and 4-bit addressing that we see. And again, she actually converted the machine language back into assembly language that we can understand, more human readable language here for us. Now note, this has 4 registers, A, B, C, D here. It has an instruction register and add an instruction address register here. It has a control unit, an ALU to do some calculations. You walk through some of this, but not too much.
And stores it into register A. Then we have a load B15 instruction, which takes the value in memory location 15, which was the number 14, and saves it into register B. Okay, easy enough, but now we have an add instruction. This tells the processor to use the ALU to add 2 registers together. In this case, B and A are specified. The ordering is important because the resulting sum is saved into the second register that's specified. So in this case, the resulting sum is saved into register A. And finally, our last instruction is store A13.
Okay, what do I want you to be paying attention to when you watch this? So the first thing you want to do is compare the assembly language instructions in the video with those in part 2 here. So yeah, we want to compare that, describe at least 2 instructions that are the same in the video and in part 2 there. What I mean by the same, they don't necessarily have to be identical, but very similar. Like when we said load A, they're actually loading it into register A and we're loading it into the accumulator. And in a lot of ways, I kind of say those are similar. They're this technically slightly different, but similar. It's like add, their add and our add is, but again, I would classify those as close enough to be the same. So look through, here's our assembly language. And then watch the video and see if you can come up with examples from their assembly language that are the same or similar for that. So,
which instructs the CPU to write whatever value is in register A.
And so again, she's done a load, she's done the A, and she's done a store out here.
Yes, our program adds 2 numbers together. That's about as exciting as it gets when we only have 4 instructions to play with. So let's add.
I like how she gets excited about adding 2 numbers again together. So
some more. Now we've got a subtract function, which like add specifies 2 registers once.
Now, the other thing you want to be able to do, I keep missing where I'm at. Okay, find 2 instructions, describe 2 instructions that are same in the video as in part 2. And then the next one is describe 1 instruction that's in the video, but not in part 2 above. So find an instruction that's not in this list. No op, load A, store A, add, subtract, multiply, divide, print, input, bar for variables. So we want an instruction that's not one of those.
We've also got a fancy new instruction for jump. As the name implies, this causes the program to jump to a new location. This is useful if you want to change the order or skip some instructions. For example, a jump 0 would cause the program to go back to the beginning. At a low level, this is done by writing the value specified in the last 4 bits into the instruction address register, overwriting the current value. We've also added a special version of jump called jump negative. This only jumps the program if the ALU's negative flag is set to true. As we talked about in episode 5, the negative flag is only set when the result of an act.
Okay, now remember when we were talking about in the book about the fetch execute cycle here. And again, we talked about we fetch the next instruction while we initialize the program counter, which again, the instruction counter, we fetch the instruction, decode it, and then again, if it's a branch instruction, all we do is update the program counter and fetch it again. Otherwise, you'd execute. And so like these jump instructions, those are the branch instructions. And again, sometimes they're branch if negative, sometimes they're just jump, always jump here. This is how we do create loops or decisions in our program here. Okay. I'm not going to play this it's a whole 10-minute video. I think it's a great video. They talk some point about the ALU. We'll actually play the ALU video or have you watch that later on. Again, when we get to the adder and stuff like that and talk about some of the flags and how the ALU works. But this mainly focuses on, again, the CPU and walks you in more of that.
Register A, 5 gets loaded in from register B. Now we subtract register B from register A. That's 11 minus 5, which is 6. And so 6 gets.
Okay. So I'm going to let you do that. And again, let you watch the rest of that video on your own. Okay, now the next thing we're going to talk about is addressing here. With our instruction sets. And some of these complex instruction sets will have a number of addressing modes. And you can see why some of these will require more than one clock tick to do them here. So we're going to talk about immediate addressing here, where we'll load and we'll load. So just giving addresses kind of directly or stuff. And we'll have you learn more about these and how walk through these commands in just a sec. So there's immediate addressing here. There's absolute addressing, and it's kind of confusing at first. What's the difference between immediate addressing and absolute addressing? Absolute addressing will specify an absolute address here. So isn't that what immediate addressing was doing, you were saying? So you want to try to understand the difference between those two. When we write these out, you might see some slightly different versions of these stuff. So we have absolute addressing here. We have absolute index addressing. So again, notice with absolute addressing, it was $$ and then the address. It's kind of a weird thing, but $$ and then the address here. With index addressing, it is just $$ here. So like $ and address, I think, is what we're specifying. So we'll talk about what this is here. So with index addressing, we generally have an offset from a location here. When we do programming a lot, we often work with, like, let's say an image, and we'll want to manipulate the image, and the image will start at some location in memory. And then if you want the, pixel 20 of the image, you want to go over 20 bits from that starting location in memory. So you want to be able to load up the starting location of the picture and then index the memory based on that, so that wherever the image is located, your code will work as long as you set that first starting spot in memory. We also use what are called arrays a lot, or lists. So we'll load an array, a list of integers into memory. And then when we want to read like the fourth integer in the list, we'll say, oh, that's the beginning of the list address plus 4. It's a little more complicated, but because it's not just plus 4, it's plus 4 times whatever size. So if an integer takes 32 bits, the address would be like the starting location plus 4, the fourth digit times 32 bits for each digit or something like that. But again, the computer can take care of that. But we do a lot of places where we'll index memory off of some starting location for this stuff. And then there's also indirect indexed memory here that you want to look at. And again, you'll start looking at this and seeing that some of these are going to take more than one memory address, because now we can't just load in a memory when we have an address. We don't have to just load in a memory address. We have to load in a val. So like here, so we are a 2-bit address stored in a memory address. as the base address adds the contents of the Y register to produce a new address. So we have a whatever's in the Y register plus whatever address is in this other location. So we have to first we load the instruction, then we have to interpret the instruction. And the first thing is there's a memory address that stores the memory address we want to use. So we have to do another fetch to get that next memory address in from that memory location. So now we have a new memory address. And then we have to actually, to get the address, we have to add that to whatever the base address is in the Y register. So we have to do another execute to add the two memory addresses together. And that gives us our final memory address. And then once we have that final memory address, we will read that final memory address in the memory. And then we actually do our add or whatever we want to do. So just to get the right value in the memory might take a couple clock cycles to execute here. Now you're thinking, Tom, you do not explain that very well. I wish I had something better to explain that to you. Okay, we'll do that. So in the exercise for part 4, we want you to go over these 4 types of addressing. So we want you to ask AI to explain this here, like what this code does, and summarize the response here. And try to walk through where in RAM and what the registers might be. So here. So I want you to bring up, I don't think I linked to AI here. I should add AI. So you can pick your favorite AI. Do you have a favorite AI? Out there. So again, you can go to ChatGPT is again probably the most popular one out there. You can go to Gemini. But one thing with Google Gemini is for me, it's still blocked on campus with my Gmail account. So if I go to Gemini, it says, and I'm working with the college to unblock that, but it's still out there. But I know if you have another Gmail, I don't have my other account. If you have another Gmail account that you're logged in, Gemini will work fine for free. So I, like on my other computers, I just keep another Gmail account logged in to use Gemini. You can go to Copilot by Microsoft here. What's the new, have you guys been following the new one that came out this weekend? Deep what? Seek. That's the newest one here. It just blew up over the weekend so much for it that so far today I haven't been able to use it. So due to they're saying that they have some things. So when I log in, I just log in with my school Gmail account. And I can do it. But so let's try this out. If I just take this and paste it in here, how is it gonna do? It's fast. A lot today was so overwhelmed that it was failing on everything I put into it. So you have to see if it responds. There. There's perplexity. There's I remember some other ones out there you can use, but use any AI you want here. Have it explain the results and post the summary in here for this. And then try to walk through that and try to figure out what's in these different RAM addresses for that. So. Okay, so hopefully you go through and learn a little bit about these addressing modes here. So again, immediate addressing is when we just provide the number. We're not actually addressing, we just say add 4 or add 7 to the thing. Absolute addressing is when we provide the number there. Index addressing is based on this index, and again, otherwise, and then the indirect addressing is when we store the address in another location in memory. So we have to load the memory address in, and then we have to add, then we use that as index addressing here for this. So now text walks through some other instructions here. Again, this isn't going to be an assembly language instruction thing. There are some standard instructions: add, subtract here, increment, decrement here, different types of increment. The increment a register, decrement a register here, X and Y for registers or stuff like that. Here, compare. There are logical instructions like we just looked at, and, or, XOR. Here is often wrote maybe EOR rather than XO. I don't know why it's not XOR, but the instructions often EOR for this. There's these branching instructions, the jump instructions, different types of jump instructions. There's also this whole area of subroutines and instructions. So some assembly language has subroutine instructions where you can call a subroutine and get access to it. Other ones will just have you do that yourself with the jump instruction for this. Same with loops. Someone will have some sort of simple primitive loop, but a lot of times assembly languages will just have a jump, like a jump if negative instruction. And then you have to set up your loop so that it just uses that jump instruction for that. So there's a whole process with interrupts where the process is going through the fetch execute cycle and some interrupt occurs. I'm not gonna worry or talk at all about interrupts really. So we're just gonna ignore interrupts for this stuff. So most of the second part of this instructions here, when you get down to interrupts on, we're just going to ignore in this class for this. So. I think that's the end of your instructions here too. So again, remember here, every week you have to do an activity, an explore activity. We are starting a couple longer ones, exploring some cloud architecture stuff. Again, we're going to have you go through these, and we're not really going to talk about them too much in class for another couple weeks here. And then we'll actually we'll get to the Raspberry Pi where we're treating the Pi like in a cloud, and or we're doing commands to it. So in a couple weeks, we'll start doing more cloud stuff in the labs, and this will start making sense. But for now, you're just doing the cloud stuff kind of in prep for that. And again, you can do any of these three options. They're all part of longer things. And again, in future units, we'll jump through these other ones. So again, you can jump back and forth, or you can just pick one of these, like the Microsoft. You can do the part 1 this week. I think part 2 is next week. Part 3, I don't think we do part 4 in this class, but again, you can do that on your own if you want to do this full series and get that. So you can do one of those, and then for the lab, we'll be doing that. The lab is going to be pretty full. We'll be doing programming Python for the first time. We'll talk a little bit about assembly language, but then we'll do Python. I don't think you probably had Python yet. So what kind of programming have you all had here? So some of you, a lot of you have been through CS principles and you've done block programming where you drag the blocks, right? So you've seen that, so that's good, here. Not if you if you've had Java 1. Some of you've had Java 1, so some of you've had Java 1. So that'll help you, but that's in Java, not Python here. So you have to see that. So we're not going to teach you a lot of Python, just enough to be dangerous here with this. So I'll tend to provide you the Python and then you can tweak it just a little bit. But since it's not a programming course, I'll generally provide you the Python for this. But again, you can, if you're interested in Python, once you start learning, you can ask AI or something to explain this Python program to me in more detail. So you can decide if you want to dive into Python a little bit more. But we'll be using Python. So in the lab, we'll set up the same sort of LED light, remember that was on. We'll then program it in so that we can write a program to make the light blink or blink when we hit a button or something like that. So we'll be able to control that LED with code. That's our whole job will be on Thursday, is to do that. Okay? So we'll do that on Thursday. I'll let you, I'll stop this now. I'll let you work through I'll stay around if you have questions about. Well, any questions before, like, do you have right now on this exercise? Okay, I'll let you go through the exercise, watch the video. I'll stay here if you have any questions. I'm going to stop the recording here.